The next talk, Ming Xiaoli will give the next talk. He is a PhD student at KU Leuven in his last year. So,
okay,
yeah.
So hello everyone. I'm going to present our work on enhancing neural networks through common-sense reasoning. So as humans, we have a lot of common sense about the world, and this can help us to do a lot of reasonings. For example, if we see an animal in the sky, we know it's definitely not a dog or a cat because both dog and cats cannot fly. And in this research, we try to see if we can be a human-like intelligent agent to also conduct a reasoning with the help of external knowledges. And in our research, we select two types of knowledges. The first one is structural knowledge. For example, the concept net. Each knowledge in concept net is a triplet containing subjects, objects, and relations. And the second one is the implicit knowledges. In here, we mean the knowledge learned in pre-trained models. And more specifically, we mean the text-to-image generative models. And we conduct our research on two tasks. The first one is the knowledge-based visual question answering, and the second one is remote object grounding. So what is knowledge-based visual question answering? In this task, given an images, a knowledge base, and a questions, and we ask the agent to answer the question correctly. And to answer the question correctly, the agent needs to first extract related knowledge from the knowledge base, and then it has to understand the images, including all the objects in the image and the relations between objects in the images. And there are two challenges in this task. The first one is how to integrate external knowledges into models. So here we mean the knowledge in the knowledge base. And the second one is how to handle multi-step reasoning questions. So what is multi-step reasoning? Let's take a look at these questions. What's the relation of the tree and the object that belongs to the class of mammals in the images? To answer these questions, in the first step, the agent has to understand what objects in the images belongs to the class of mammals. And in the second step, it has to reason the relation between the trees and these objects. And here shows the overall pipeline of our solutions. The first is the image representations. How can we represent the images? We use a graph to represent the images. Each node in the graph represents the objects in the images. And then the edges between two nodes are the relative spatial information of the objects in the images. Second is how can we represent the knowledges? So we have the knowledge base, and then we use the graph or the embedding to represent each component of a triplet. And then we use the information retrieval techniques, also the question embeddings to retrieve related knowledge from the knowledge base. So in our solutions, we first use the neural networks to get the question representations. And then we use this representation to guide the image graph to update its node representation and edge representations. And then this graph representation is further used to update our question representations. And we have another question guided memory readings. So we use the question representations to gather useful information from our memory modules. And then during inference, we first decide a predefined number of reasoning steps, and then we do these two reasoning steps recursive until last it outputs the answers. And here shows the details of each component. So the first is the memory readings. So the memory module is designed to store the knowledge information extracted from the knowledge base. And then the module contains two parts. The first one is the key. The second one is the values. And for the value, it's just the graph embedding of each component in a triplet. And the key embedding is the average embedding of three components of a triplet. So first, we used our question representations to conduct close attention over the value embeddings to get a representation for each triplet. And then second, we used the question representation to compute the attention score over the key embeddings. And then we just compute the weighted sum of these two to get the final knowledge representations. And this representation is further used to update our question representations. And in the second step, the graph reasonings, we have the question representations, and then we use the representation to guide the graph map, the graph to do the graph convolutions to update its node embedding and also the edge embeddings. And then this graph embeddings is further used to update our question representations. So after these two steps, we will obtain knowledge area and graph area question representations. And then we finally use this representation to output the final answers. And here shows our results. We test our model on two datasets, KRV-QR and FVQA datasets. So we obtained the new state-of-the-art performance on both datasets. And more specifically for the KRV-QR dataset, our model surpassed the previous SOTA model by around 60%. And follow the previous literatures, we also try to integrate our model with dense captioning models. So we use dense captioning models to generate dense captions of images. And then once we have all the captions of the images, we build a concept net, and we integrate this concept net into our model as how we integrate the image graph to the models. And this result shows that integrating the dense captioning models to our models can further improve our model's performance on both datasets. To verify the effectiveness of our proposed modules, we conduct several operation studies. And then we do our operation study on the KRV-QR dataset. So the first is, does the number of reasoning steps really matters? And here shows the performance of our models when we conduct different number of reasoning steps. And this shows that our model with two-step reasonings achieves the best performance. And this is not surprising because when we look at the dataset, we found most of samples in the dataset only needs two-step reasonings, like the example I showed in the first slide. And doing more reasoning steps might confuse our models, so the performance drops. The second question is does our proposed key value memory really help? In these experiments, we replaced our key value memory by two other methods. The first one is the average embedding memory modules. Next, we use the average embedding of a triplet as the embedding of the knowledge triplet. The second one is the key value memory modules. Then the key is the embedding of the subjects and the relations, and the value is the embedding of the objects. And the last one is our models. So our proposed the key value memory modules outperforms the other two modules. And the last one is the external knowledge really helps. And obviously it's help because some of the knowledge alone appears in the images, like the first questions, like the first example I showed before. There's no information in the image showing which animal belongs to the class of mammals. And here is some attention visualization of our models. We want to see if our model can do the reasoning in a logical ways. So let's take a look at the bottom left samples. Here shows the attention weights on the knowledge triplet. The question is, what is the relation of players and the objects that is more popular than tennis in these photos? And then we can see the soccer has the highest attention weights. And here is the attention weights on the image graphers. Here, the football has the highest attention weights. So this attention visualization shows that our models can understand the knowledge and also the images, and then do the reasoning in a logical ways. And the second one is the second research is like the remote grounding task. So in this task, given an agent, and then we given an agent, we put the agent in an environment, and the environment could be a house, a hotel, or hospitals. And then we give a high-level instruction to the agents, and we ask the agent to follow our instructions to find the correct objects. For example, like the instruction shown here, go to the second neighborhood just outside the bedroom and turn off the lights. Then we hope the agent can go to the right locations and then find the right objects. So as the agent could be anywhere at the beginning in the environment, so to correctly find the objects, it has to navigate to the positions where the objects refer to in the instructions. And also the agent has to identify the correct objects among all the visible objects in the location where it stops. And there are two challenges in this task. The first one is how to effectively explore the environments. The second one is how to better generalize to previously unseen environments. And this is our baseline models, our models. The first is the baseline models. First, we use a graph to represent the environments, and the model has to build this map on the fly. That means at the beginning, there's only one node in this graph first. And then when the model takes one step, then it will gather the information from the environments and add more nodes to the graph first. It has to build this graph on the fly. And then in the baseline model, there are two branches. The first one is local branch. The second one is global branch. So for the local branch, the agent has to select the next step from all the labeling steps of current locations. And in the global branch, the agent can select any nodes in the map. By doing so, that we allow the model to do the self-corrections. That means it can go back to the previous steps and then find another way to go to the locations, the final locations. And then finally, we will try to merge the decision of the local branch and the global branch to make our final predictions. In this task, we propose two modules to tackle two challenges I mentioned previously. So first is the Go Dreamer branch. This is inspired by how humans solve these problems. So as a human, when we obtain these instructions, enter the bathroom with the red and the black words and turn on the things, we could imagine the locations first, and then we can make our decisions. So in this branch, we use the text-to-image generation models to generate 5 images of the target locations. And then we use clip visual encoder to get a visual representations. And we use this representation to help the model to make the decision for next steps. The second branch is the layout learners. So this module aims to learn to infer the room category distribution of labeling unexplored areas along the path. In this branch, we try to ask the agent to predict the room categories of all the nodes in the map. And then once the agent takes one step, it has to update its predictions of all nodes. There are many ways to do these classifications. For example, you can just use a classification head, linear layer to do the classifications. But here we will try to introduce the visual Commonsense knowledge to the models. We use the text-to-image generative model to generate 5 to 6 images for each room type. And then we use the clip visual encoder to get the embeddings of each room type. And during prediction, we just compute the similarity score between each representation, the representation of the room type and the representation of the node. And the one with the highest score are the predictions. And here shows our results. So our model obtained a comparable performance on the same validation environments, but on the unseen validation environments and the unseen tested environments, our model has much better performance on the successful rate and also the grounding accuracies. We test our model on 2 datasets. The first one is the river, the second one is the swing dataset. And then we have the similar observations here. Next is the operation study. So the first is, are the learners and the Go Dreamer really help? During these experiments, we remove each of our proposed branches, and then we compare their results. And here we see, by just adding each of our proposed branches, can already improve the performance of the baseline models. And then further adding our proposed branches to the models can further improve the performance of the baseline model. The second is visual textual Commonsense. So in the layout learners, we use the visual information to do the classifications. And in these experiments, we have two different operations. The first is if we just use a classification head. The second is we use a sentence to describe each room type, and then we get the text embeddings, and then the same we compute a similarity score between the node embedding and also the text embeddings. And then here shows that our visual classification head achieves the best performance. The last one is like room type corrections. So in our design, we ask the model to update its prediction of the room time every time it takes a step, because we hope when the model gets more information around the environments, it should be able to have more accurate prediction of the room time. For example, if the model already passed the kitchens, then probably it knows next room should not be the kitchens. And by doing so, we do this experiment by test the prediction accuracy versus the time steps the agent takes. And here we see when the agent takes more steps, it has more accurate prediction of the room time of the environments. Next is the visualizations. How do our model correct its predictions? So the red arrows are the right path the agent takes, and then the double circle are the current locations. So in the first images, the model predicts the location of alpha is an office, but the ground truth is a bedrooms. And then when it takes one more step, then it changes predictions to living rooms. And then when it takes another more steps, then it changes it to bedroom. Then this is a correct predictions. So this experiment shows that when our models has more information about the environments, it can better predict the room types. So yes, that's it. Yeah. So that's all my presentations.
Thank you. Do you have any questions? I would have a question. I saw that you use Glide in the two modules. I'm talking about the second paper.
Yeah.
Was it a reason why you chose Glide instead of other text-to-image models?
Because when we did this, when we started this project, Glide is the best text-to-image generative models.
Okay.
There wasn't like Stable Diffusion or DALL-E. There wasn't that.
At the time when you wrote the paper.
Yeah.
Okay.
Yeah.
That makes sense.
Also, it's open source. Yeah.
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 Thank you.
Yeah.
How long it takes to build the data set and the graph network?
Which data set?
The data set and the layout network.
Oh, you mean how long can we
Yeah, and how the efforts.
to generate those images?
Yeah.
It depends on how big is the data set. So I think it takes, like we use, Glide is also like diffusion based. So we use like 15 steps, 50 region inference steps to generate the images. I think it takes around 1 day to generate the images for all the locations in the data set. Yeah, so.
I'm also not sure about the action prediction. It might happen that during the inference to observe another action than the one that the model is trained. So is this possibility?
So
I'm not sure what is happening with the action prediction.
Yeah, so the action space is fixed. So you can move forward or turn left or turn right.
Okay.
The
So
action
these are the
space is fixed.
Mm.
Yeah.
Okay.